Hey, hello there. We're going to talk about our first section, which is on tangent lines to circles. So a tangent to a circle is a line that intersects a circle at only one point. If it intersects at more than one point, it's called a secant, but we only care about tangents for now. So they intersect at one point. So we can make a sentence that says AB, line AB, is tangent to circle O. And we can use that symbol for circle. We name a circle by its center. Okay. A point of tangency is what you might think. It's the point where a circle and a tangent line intersect. Okay? So I could finish my sentence and say that line AB is tangent to circle O at point P, where this is a point of tangency. Okay? So the first thing that we're going to learn is that when you have a tangent line, it creates a right angle. And that's all theorem 12.1 is saying, is if you have a tangent, then it has a right angle. Okay? And the next theorem is pretty simple. It's just the other way around. If you do have a right angle forming with a radius and a tangent, if the right angle is there, then we can call it a tangent, right? So if a line meets a circle there at one point at a right angle, it's tangent. Basically, all you need to know is that you don't even really need to worry too much about this because it's all summarized by going both directions on this first one. Okay, so it's up to you how you want to look at that. But basically, tangents meet at right angles, which is 90 degrees. So that allows us to solve a number of questions here. So I'll kind of try and leave that up there for you. So here we have two tangents to O, circle O. Yeah, they should say circle O, sorry. Circle. What's the value of x? Well, we know these are right angles because it said they're tangents. So we also know that this shape here is made up of a triangle with 180 degrees and another triangle with 180 degrees. So MNOL or LMNO has 360 degrees of internal angle. So when I start adding this up, I can make an equation 117 plus 90 plus x is 360 degrees. Okay, so a four-sided figure, the angle's added to 360. So all of these numbers here add together to 297. So I can just go ahead and subtract and get 63. All right. Same deal here. That should say circle. I'm not sure why it says point. What is the value of x again? Well, we know this is a right angle, so we can think of the angle argument again, right? 38 plus 90 plus x must be the angles of a triangle, which is 180, right? And if we combine this and solve for x, we get 52. Okay, so basically tangents are at right angles is our goal here. You could also find, so you can find angle measures, but now we can also find a radius here. So what is the radius of circle C? Well, first things first is it's showing us that this is a right angle. So we could definitely set up Pythagorean Theorem of this triangle. Now, this is a little weird, but we're going to do leg squared plus leg squared, right? Because it is going to be a squared plus b squared equals c squared. So it's the small leg plus the small leg squared plus the small leg squared equals the big leg squared. But the big leg is actually x plus 8. All right, so we need to hop back to algebra class and remember, hey, how do I handle something that looks like that? And it's foiling. So what we're going to do is write it as 2 copies of itself. And then we're going to distribute, or we use the acronym FOIL. So that looks something, you've definitely done this before, may have been a while, but you always do the firsts, the outers, the inners, and the last. That stands for FOIL. And you multiply, it's like distributing. So this is going to be x squared plus 8x plus 8x plus 64. Okay, if you're unsure on that, I would just, Google up a video of how to FOIL, and you can see some more examples of that too. We're going to do another example too, but it's just distributing, you just kind of do it twice. All right, so what happens now? Well, I'll combine like terms, and I want to solve for x, and I notice I have x squared on both sides, so that just cancels. And I'm left with, I'm going to subtract the 64, get the x's alone, numbers on the other side, and we get x is 5. All right, so the radius of that circle is 5. And notice that you can draw a radius in more than one spot, like every radii, or every radius is equal. Okay, so let's do that process again and see that foiling again on another example. So again, this is my A, this is my B, my C is going to be my largest side. So A is X, B is 10, and C is going to be X plus 6. So I've set up Pythagorean Theorem, make this 100, and let's rewrite both of our copies. And we're going to FOIL again. So let's do this. So x times x is x squared. X times 6 is 6x. And then my inners, 6x, and my outers, my final, the L, the last, is 36. Okay? So I like to combine like terms on both sides and then assess what we have. So I do see again the x squareds cancel, and I want to move that 36 over and get 64. We get kind of a weird answer here, 64 over 12, but we could write that as a decimal. I'll be more clear in the instructions on the test, like what you need to do, but it's 5.333, so that's x. All right, so that's all just using these first 2 theorems. Basically just saying that a tangent is 90 degrees, and if you have something that is 90 degrees, that's a tangent. Okay, that's what converse means, is going the opposite direction. So taking this and going this way, assuming the last one and proving the first one. All right, so another thing that we can use that theorem for is identifying a tangent. So the question is ML tangent to circle N at the point of tangency L? I don't know. If we can prove that there's a right angle, then that means tangent, because right now there isn't a right angle there. So how do we prove that a triangle is right? Well, if it obeys the Pythagorean theorem, it's a right triangle. The Pythagorean theorem also goes the other way. Normally it's if you have a right triangle, then a squared plus b squared equals c squared. But it also goes the other way. If a squared plus b squared equals c squared, you have a right triangle. So what we're going to do is test and see, does this work? is this true? And I'll save you the heartache of having to square all of that. This gets us down to this equation, which is of course true. So yes, it's a right angle. And with that right angle, the answer to this is yes, because a tangent makes a right angle with the radius there. Okay. New theorem. This one's kind of cool. So if BA and BC, those red lines, are tangent, then we have that they're equal in length, that they're congruent, right? So both of these are congruent somehow. Okay, so that is really interesting that they meet at point, they intersect. I called it the intersecting tangents theorem because they both intersect at B, right? And they turn out to be the same length. So I thought it would be a good start to try and prove this. So I've written it all down here for us, and then we'll do those two examples. So again, we have two tangents to circle O, and we want to prove that these two red lines are congruent. Okay, so let's see what the argument goes by, and we'll give all the reasons for it. So this is given. It says that angle A and angle C are right angles. So the picture actually wasn't perfect. We needed to draw those in there. And then we can see angle A. They're saying that this is the case, that we have right angles there. Now, why would they believe this? Well, the only thing we have to go off of is the word tangent, right? So this is I would call this the definition of tangent. You could also cite the theorem, which would be this one, right here. Because we have that it's tangent, and we want to show that it's a right angle. So that's exactly what theorem 12.1 gives us. Okay, but I'm okay there with like definition of tangent. I don't know if we're going to do proofs on the test or not. They're not going to be crazy if there are. So don't worry too much about citing all the special numbers and everything. They're more just for like inside the lesson, so we know what we're talking about. All right, anyhow, it says OB is congruent to OB. We don't even have OB drawn, but it would look something like that. And this might be setting up two triangles. Now we can kind of see the direction this is going. But that is backed up by the reflexive property of congruence. And AO, the next one, AO and CO, those are both radii of the circle. So not only are not only is OB congruent to itself, but these two radii or radiuses are congruent to themselves too. Why? Because all radii are congruent in circle O. You know, if I pulled up another circle, then they're not going to be same to those, but within that circle, all the radii are the same. You know, if I drew this big circle here, the radii of that circle don't match the radius of circle O, but we're not looking at that circle. We're just looking at the same circle here. So now it's making a statement about triangle congruence. So we have to go back to chapter 4 and think, hey, why are these triangles equal? And we had 5 things that we used for that. We had SSS, SAS, ASA, and AAS, but the final kicker was the hypotenuse leg theorem. And if you look here, we got right triangles, so maybe we should consider hypotenuse leg. So remember, hypotenuse leg, put these down there. Hypotenuse leg requires 3 things. It requires 1, a right angle, or right angles, 2, a congruent hypotenuse, and 3, a congruent leg. That's why it's called hypotenuse leg, and it works with right triangles. And that's exactly what we have. We have 2 right triangles with the same hypotenuse and the same leg. So those triangles are the same by the hypotenuse leg theorem. And finally, we have what we want to prove, that these 2 orange or red orange, they look orange now. These 2, we wanted to show that those are congruent. And we have enough to show that because those 2 triangles are congruent, right? And that's the long leg of those triangles. So because the triangles are congruent, long leg and long leg are going to match up, right? So we had a name for that. That was corresponding parts of congruent triangles are congruent. And that long leg is a corresponding part. We have 2 long legs, and we know the triangles are congruent, so those got to be congruent too. So this is a way to show that when you have tangency like this, and you have tangents that meet outside, those 2 tangents are the same length. So we can put little prime marks there, okay? So we can have a lot of tangents going on. So for this one, it says we have a circle inside. Inscribed means that it perfectly fits on the inside and that it touches only at one point. So that basically is telling us that, hey, all of these are points of tangency. So our last theorem holds. So basically 10 is going to be equal to 10 over here. 8 is going to be equal to 8 over here. And 15 is going to be equal to 15 over here. Right? Because that's what, if this was, 17, this would be 17. So that's what we're doing here is we're using theorem 12.3. Okay? What's the perimeter? Well, the perimeter is the distance around. So all I'm going to do is I'll start right here, and I'm going to go around my triangle, my triangle, and add up all of those numbers. So it's going to be 10 plus 15 plus 15 plus 8 plus 8 plus 10. And that is 66 or 64? 66, I think. For some reason, I thought 8 plus 8 was 14. That's not right. So anyways, whatever that is, hopefully that's right. That's our answer. All right. So kind of neat, right? We can find out all these. I mean, we have a ton of info. Like, that's a really big statement that those are equal. And we just proved it. So you could do this again. If you have a circle on the inside of a triangle, this time you know the perimeter, so you know it's 88, but you have some missing sides. It looks like QY. We will call that X. And of course, since we have tangency, this is also X, right? And this 15 is this 15, and 17 is 17. So it's kind of like this little TP that's happening here. It starts at 2 points on the circle, and it kind of meets up and makes this little hat, right? This party hat. And both the sides of that party hat are equal, is what we just proved. So I'm going to go around the triangle again. 15 plus X plus 17 plus 17 plus 15. I think I went around like this. There should be 6. Let's see. We have 64 plus 2x. And then I'm going to go ahead and move that over. And you guys know how this works. We solve so many equations together. That would be our answer. And then we want to include centimeters. Okay, so those 3 theorems are kind of it, and you should just know how to apply them. The homework here is really short, but make sure you go through it. I don't think there'll be any struggles, but these are the notes.